learning, if you see what we have got, we are actually having a computer which is still the same, but this time I've got inputs that I'm giving in the form of data. So this input over here is some data, and this output, as you can see, that instead of expecting an output from the computer as in the previous case, we are now actually feeding in output. So what we are saying is that for a given particular data, for some given data, which is an input, I also know that this is the expected output. So both of them are known to me. And I feed in both to this computer, allowing the computer now to actually generate the rules themselves. So this is a major shift in paradigm. Instead of having to write our own rules, we can now get the machine to write these rules. And if you've got sufficient amount of data to go in, if you've got sufficient amount of inputs and outputs to go in, then the machine can actually generate rules which are highly effective and often something that even a common person with domain expertise in that field may miss. So machine learning, as I said, has turned the concept of programming on its head. So where instead of feeding the computer what to do, we are now feeding the computer just data. The interesting side aspect of this is with the influence of the internet and the burgeoning amount of data that is now available, we are in a position to feed huge amount of data into a computer. So that means this input and output is virtually limitless nowadays. And machines actually thrive on this. The more input and output you give it, the better these rules keep on getting. And because of the amount of data that is now available through IoT and sensors and even text that is available digitally, the amount of data that is available to computers is tremendous. So obviously, the rules are also getting better and better for each domain-specific task, right? Given that we have just gone through this definition, let us be a little bit formal and try to define what machine learning is in a slightly more infrastructural framework. So if you see, Arthur Samuel, even in 1959, and you can see machine learning has a long hierarchy. You can see he defined machine learning as the field of study that gives computers the ability to learn without being explicitly programmed, and that is very, very important. So he could say, even in 1959, that there would be a time when programs would not have to be written and yet machines would be able to learn things, right? And then this definition was actually improved by Tom Mitchell in 1997 in his very, very famous book on machine learning, in where he says that a computer program is said to learn from experience. And we must be very particular that he formalized these concepts. So he said that E is the experience with respect to some task T and some performance measure P. So he defined three things. He said that there must be some experience, there must be a task which is well defined, and there must be some performance measure. And the machine actually has to increase on this performance measure as he keeps on repeating this task. So the idea was every time the machine does this task and he fails to get the correct answer, he gains some experience. And after he gains this experience, he retries the task, and now his performance should increase. And he keep on doing this in an iterative loop sense, and sooner or later, you will be able to get this performance measure to a desired threshold. So Mitchell in his book actually made it very formal by saying that for a machine learning environment, you must have some kind of an experience, you must have a well-defined task, and then you must have a well-defined performance measure. So this is how Mitchell described machine learning in 1997. Right? Now, let's get, I think I'm getting some echo back. I think someone's mic is on. Right. So
maybe someone, please mute your mic.
Right. Thank you. So now that we have seen the formal way of talking of machine learning, let us very quickly see how you are going to write your machine learning programs. So let's first start off by looking at the traditional approach. So this is how we have been writing programs for the last 60, 70 years in computer science. So we start by looking at a problem, and then having analyzed the problem either through the expertise of a computer programmer or through domain expertise, we end up writing some rules. So these rules will usually be in the form, if I am permitted to write some C code, let's say, they will usually be in the form of if condition, and then you will write some code, do this, else if condition, do this. And that is how we have programmed computers for 60, 70 years now. So having analyzed a problem, we write our rules, and then we apply those rules and see if the rules are giving us the correct output. And we keep on analyzing the errors. Obviously, the errors must be creeping in because our rules are suspect. So every time you don't get a desired output, you go back and check your rules. And you check your rules and rerun the program and see if the output is correct. At some point, obviously, you will be happy with the program, and then you will actually leave that program to run for the audience. This is how we have always written our programs. See some program, get some rules written, evaluate how good the rules are, make changes to the rules, keep on iterating, and finally, when you're happy, launch the program for others. Right? So this has been our traditional approach. Mark the fact that in this approach, there does not seem to be a lot of data entry. Right? Now, if I go back now to the machine learning approach, how machine learning has changed this playing field. We are studying the problem, we are trying to understand that, so that's common. But this time we have access to data. We've got a lot of data at hand. And then we feed the data and the problem understanding into a machine learning system. And you see that we are at no point are we trying to write rules. Now the rules would be written by this machine learning system itself, by this machine learning algorithm, based on the analysis of what is to be done and the data that is available. Once the rules have been written, we can evaluate the rules on some data set. And if I find that the outputs of these rules are completely in sync with what we are expecting, then the program gets launched. However, if we find that the rules have still not learned what is to be learned, we keep on iterating this in a very simple loop. So feed in data, train this algorithm, the algorithm learns some rules. Are these rules acceptable? If yes, then you launch the program. If no, then you keep on analyzing and get better rules from the machine learning system. The crux of the matter is, in this particular machine learning approach, the focus has completely shifted to this part over here, which was completely not there in the previous case. You see, there is no data over here. In machine learning, as we have said, and we keep on saying, in machine learning, we keep on saying that data is king. So the more data you have, the more correct data you have got, the machine learning algorithms will work better and better. Right? Now, the question that is often asked by the community is, why is the machine learning approach actually winning over traditional algorithms? Now, be very specific. When I say it is winning, this is not a situation where I can say that it is winning in all cases. It is winning in a lot of cases, but there would be application areas and verticals where I don't think machine learning would ever get applied. Say, for example, just to go into a slightly CS kind of a talk, if you're trying to design an operating system, now I don't think an entire operating system is ever going to get designed using machine learning. Some of the components of an operating system may get optimized using machine learning. That's a different issue. But we are not looking at completely designing an operating system using machine learning in the near future. But there are other tasks where machine learning will completely outperform traditional learning. The reasons for this, why they actually are so much better in some tasks, is because some tasks are just too complicated to write rules. Say, for example, human vision. This is an inherent ability that we are born with. And till date, we understand human vision only very, very abstractly. It is very, very difficult to actually completely write unambiguous rules to explain how the human vision system is working. And even if you are able to write rules, we will never be able to get them to work at the speed with which the human eye works. So the fact remains, some tasks, even though they seem latently easy, in terms of concrete unambiguous steps, they are very, very difficult. The second thing that makes machine learning very attractive is the fact that when new data comes in or some expected output changes, in a manual system, you are supposed to write the new rules. So you have to constantly be ready in the old traditional form of coding to write these new rules. But in a machine learning system, as soon as your data starts to change, the machine learning system adapts itself and it can learn these new rules by itself. Another reason why machine learning is so very attractive is if programs have used a rule that has been manually written. So if you have got a system that has been using manual rules through coding for, let's say, 20, 30 years, then this set of rules becomes very difficult to maintain. So as the years go by, when new programmers join the team, they will find it very difficult to understand why a rule was written the way it has been written, particularly for complex tasks. On the other hand, machine learning doesn't have this kind of a drawback because no one is actually ever going to write the rules. The only entity that is going to write the rules is the machine itself. So you keep on feeding data and the machine keeps on writing the rules, or at least creating the rules internally. Finally, we find that traditional programs are often difficult to scale. What that implies is if your traditional program is good to work with a few gigabytes of data or maybe some MB of data, then it will be virtually impossible for a traditional program to certainly work with, let's say, an exabyte of data, or maybe even a tetrabyte of data. So when the data actually goes to huge amounts, traditional programs find it very, very difficult to scale. Machine learning doesn't have that issue, provided we do it correctly, which we'll discuss in a few slides' time. But the amount of data is actually a boon to machine learning rather than a bane. Right? But for traditional programs, it's very difficult to say so. So if the data increases, traditional programs start to struggle. So what we are basically saying is machine learning is a system which can virtually automate itself. You don't really have to spend time trying to write new rules, trying to maintain old rules, or trying to come up with a fresh understanding. As long as you have got data and you can constantly feed the data in, you see this cycle over here is virtually automatic. You just train your algorithm and keep on using it as long as you have got your current data. If some new data starts to come up, if you got some new data that is starting to come up, just add them over here. And this machine learning system, this system over here, will surely find out about this new data and update the rules. So that is why machine learning is so very attractive in many, many fronts, right? One of the things that also need to be answered at this point in time is, as I said, machine learning may not be the best alternative for all kinds of programs, but certainly going to be a very, very good alternative for certain kinds of programs. So for the community, it is very, very important. Say, for example, if I have got someone who's from the remote sensing background or someone from the electronics background, then it is very important for the community to understand what kind of an environment machine learning programs are most suited for, right? So the answer to that, if you've got a system which contains a very long list of rules, it's a very complex system, and you often find that even to get the system to do a very small thing, maybe you're having to write hundreds of rules. Immediately, you should start thinking of machine learning systems. A very important application in this domain is something called formal methods. Or say, for example, one of the things that you can say where this can be used is something called theorem solving. So we know in mathematics there is the concept of theorems. We learn all these theorems from our very childhood, and we know how to prove them. We can look at a theorem and say that we can prove this theorem, but it's a very difficult task for a computer to do, because even for a small theorem to be proven, you will have to write hundreds and hundreds of rules. This is the kind of system where machine learning can actively be deployed, because you don't have to write the rules. You just have to tell him that if this is happening, then this should also happen. And the machine will learn the rule. So basically, when you have complex problems for which traditional ways will not work, machine learning is a very good alternative, right? Systems where you've got fluctuating environments, where you've got a lot of data and the data is very transient and it changes a lot. And maybe you're working with some stock data and the data constantly goes up and down. Maybe you're working with some kind of a gold price data and the data goes constantly up and down. This is the kind of scenario where machine learning excels. Another very interesting aspect of doing machine learning is the fact that once your machine learning system has learned the rules, it actually allows the users to gain insight about the problem. So maybe you are a domain expert and you see that maybe you are a doctor and there is a patient who has a certain symptom and you are not aware why that symptom is occurring. You are not sure. But once you allow a machine learning program to work on it, once the program is finished, you can look at the rules and say, okay, this is the reason why this is happening. So machine learning is very, very good in some cases, even in eliminating human knowledge, particularly in case-based systems. So machine learning also has this additional advantage, right? Now, one of the things, and this is again from the application perspective, this is very, very important, is what are the different types of machine learning systems you can have? What are the different types? So basically, machine learning can be categorized as whether you are training the machine learning system with human supervision. So machine learning systems can be supervised, they can be unsupervised, they can be semi-supervised, and you can also have reinforcement learning. One of the goals of making this presentation over here is that I really want the audience to appreciate that while these words have got theoretical connotations and there is a lot of mathematics involved, but we have reached a stage where you've got programming power and you've got software available, but even though these things have got a lot of theoretical base that is required, we can apply them nowadays without really having to understand the theory. Understanding the theory is very important when you want to customize, but if you've got a straightforward vanilla case where you need an application, then we now have those powers at our disposal where you can directly apply these algorithms, and we'll try to show that to some extent. So one of the things is that we categorize machine learning systems is whether these systems are supervised by humans or they're unsupervised. The other way that we can categorize machine learning systems is whether they are online systems or batch learning systems. So we'll come to that in due course in a couple of slides. What is the difference between an online and a batch learning system? Again, these are very important differences because if you're going to apply a machine learning, then you must know that even if you've got a system and you think the algorithm that you've written should work, you may find it is not working correctly. So you have to be aware of what is the difference between doing an online mode and doing a batch learning mode, right? You should also be aware that whether your machine learning system is going to be instance-based or it's going to be model-based. Now, instance-based systems do not require a lot of learning. The learning is delayed, but they require a lot of computation when an answer is required. So they have got their advantages and disadvantages. On the other hand, model-based systems take a lot of learning, so they will spend a lot of time actually learning. But once they have learned, they will give answers very, very fast. So you've got two choices, whether you go for an instance-based system or for a model-based system. So we'll come to all these in due course. Let's see. Now, before we get to the different kinds of machine learning systems that we are talking about, let's quickly go through a little bit of terminology, because if you are going to work with machine learning and you've got a problem and you're looking at some literature that others have provided, then the literature is most likely going to contain words that you're seeing over here. And then going through this glossary very quickly, you'll be able to understand and appreciate what these terms actually mean. So when you're talking of something called a training set, that is the data that our algorithm shall learn from. That's the data that goes as input into our system, and the system is actually going to learn using this data. So that's your training data. When we talk of a data called a validation set, then the validation set is another piece of data different from the training set, which measures the improvement as the model is still learning. So it's very important, as the model is still learning, validation set allows us to understand what is the improvement we are seeing. So if you see a machine learning system and you're training it, and sometimes machine learning systems can take even months to be trained, but let's say after 10 days you find that the validation results are not that great, then you know that you really should not be spending time. You can stop and look at working with a different algorithm. So validation set is the data that allows us to measure the improvement as the model is learning. The test data is the final data that is used to measure the performance of a system once the learning has finished. A test data is used only once. So as long as you are learning, you are always comparing with the validation set. But when you're happy with the performance on the validation set, then the final analysis has to be done on a completely different set of data. And that set is called the test.
Abhijit.
Yes, sir.
Then how do we select the validation data and the test data?
Sir, we'll be there in a couple of slides.
Okay, okay.
Right, sir. Right. Now the next thing that we need to understand is what is the model? Now, as I've already said, it's not necessary that every single machine learning algorithm must have a model. It's absolutely not necessary. But the fact remains, most machine learning systems do require a model. And the model is actually this machine learning algorithm. Whatever algorithm you're actually trying to write is technically called a model. And the model usually depends on a number of parameters. Here I've written them as theta1, theta2, theta3, going up to theta n. You can have as many number of parameters as you wish. So when you hear the word, if you hear the word that someone is saying that the machine learning system is learning the model, you'll hear this very often in the machine learning community. What you're basically saying is the algorithm is actually trying to learn the best values of the parameters theta1 going up to theta n. So when you say that you're learning the model, the things that you're actually learning are these parameters. So just to give you an example, to make it slightly more context sensitive, let us say you're trying to learn a machine learning model which must predict a straight line. And let's say I write that straight line as y is equal to mx plus c, and we know from tradition that this is how a straight line is always represented. Now, the y is equal to mx plus c is actually a model that depends on two parameters. One is the slope and the other is the intercept. So if you need to learn a line, the machine learning model must learn the value of m and the value of c. So these are the parameters of the system in this particular case. Right. So all this, I don't want to get into mathematics in this discussion because it will digress from the intention of this. But when you say that the machine learning model is learning, you're basically learning the parameters. Now you'll often hear a word called hyperparameters. Hyperparameters are not essentially a part of the model. Say, for example, y is equal to mx plus c. We understand that m and c are essential for the model because you cannot create the equation of the straight line without m and c. But sometimes you may actually have other parameters which allow for a faster learning of these models. So you will learn theta1, theta n faster by manipulating these hyperparameters. So even though they are not essentially a part of the model, by manipulating these hyperparameters, your machine learning algorithm will actually end up learning faster. So the hyperparameters are very important in many cases, right? Instances are nothing but a single observation of your data. So if I look at data like this single row over here, is one instance, right? Features are just the attributes that your data has. So even though there is this one row, I've got 4 features. I've got age, salary, gender, and then credit rating. This is a very, very typical data set we use in machine learning. And when we talk of remote sensing, say for example, because this is specific to remote sensing, your data is pretty much going to be like this, even though it may not be called age, salary, gender, and so on and so forth. As you will see, the data is usually going to be in this form, or we will make it into this form. So every single instance is going to have some attributes. The class field or the label field is a special attribute, which is the field whose values you are actually trying to learn. So what that implies is, if I look at this first instance, then what we are trying to do is, given the fact that the person has an age of 45 and a salary of 67,000 and a gender of male, we are trying to predict the value that the credit rating should be high. So the idea is, if this high, low, and high was not known to me, if I had trained a machine learning model correctly, I should be able to get this prediction of high if I feed in this data 45, 67,000 and male. So the basic idea for most machine learning system is to come up with a model, as you can see over here, which is fed an instance. So ik is some instance, the kth instance. And what the model should be able to do in that case is it should be able to predict the label of the kth instance. So if you look at this data, the label for this first instance is high. So if I feed in this first instance so if ik is the first instance, if I feed that into a machine learning model, I should be able to predict high over here. That's the intention. But to make that prediction, the machine learning model has to learn these parameters theta1, theta2, theta3, and theta n. So this is what is essentially the basic terminology that goes around with machine learning systems, right? Now, quickly back to where we were when we started this. What are the different kinds of learning you can have? The first kind of learning is called supervised learning. And when you're doing a supervised learning, the idea is that the training data that you're giving in to the system to learn from already includes the desired solutions. And these are called labels. The data that you're feeding into the system already contains the desired output. You are telling the system that this is the data, and for this data, this should be the output. So if I just look at the diagram, so you see, you've got a lot of males over here, a lot of males. And for each of these males, you see, I can specify whether this is a ham male. So you see that label over there, or whether this is a spam male. So you see that label over here. So you've got this collection of emails, and for each email, whether this is spam or not spam is already given. And this is a typical example of supervised learning. The idea is, if I now give you a mail for which the label is not known to me, the model should have learned from this data and should be able to actually predict what should be the label for this particular data. Right? So this is a very, very typical scenario. This task itself is called classification. This task itself is called classification. In classification, the idea is I'm trying to predict a label. And a label usually will be a non-numeric field. So you see in this case, the label is whether the mail is a spam mail or the label is it's not a spam mail. So the task of classification will usually try to predict some kind of a label which is non-numeric. A different form of supervised learning is when you are trying to do regression, where the idea is that you've got some numeric values that you need to predict for. So you see that this data over here, has been fed into the system. And if you look at any particular data over here, it's made up of some value of y and some value of x. So that's an x, that's an y. And the data that you've fed into the system is in the form of tuples xy. So you're fed in x1, y1, you're fed in x2, y2, you're fed in xn, yn, you've fed all the data into the system. And the system would be able to come up with a model like this. The idea being, if you now give it a value of xk, for which you do not know the value of yk, you will be able to query this model. To get an answer for yk. And this is known as the task of regression, where you're trying to predict numerical values. So even though classification and regression both actually go about predicting values, in classification you will often predict class labels which are non-numeric. In regression you will predict class labels which are numeric. Right. We will take up some examples of classification in the third part of this presentation that will be specific to remote sensing, and we'll try to see if we can get those to work so that you can see it. Now, some very common supervised methods that are used widely. We've got k nearest neighbors and linear regression, logistic regression. Support vector machines were great around 10 years back. Support vector machines were thought to be the best alternative we are going to ever have. So support vector machines had a great future at one point in time, but unfortunately they turned out to be very computationally complex and inefficient. So nowadays we work more with decision trees and random forests, or we work with neural networks. In the last 15 years, neural networks have a rebirth. Neural networks are a concept that are more than 60 years old now, but over the last 15 years, with the increase in power of the computational ability and the processors and the graphic processing unit, neural networks have really re-emerged as the chief contender while doing supervised learning. Right. So all these methods are available. This first method over here, the k nearest neighbor method, is very, very simple. This is very, very simple, but this is also very effective. So usually if I am doing some kind of a classification task and I am unsure which particular method is going to work the best for this particular task, I'll often follow a very simple principle that I call benchmarking. So in a benchmarking system, what I'll do is I'll pick a very simple algorithm. Let's say I pick something like k nearest neighbor, and I'll get that algorithm to run on my problem, and then I'll see what is the actual performance metrics that is coming up. So I'll just look at the performance, and then I will use that as a benchmark. So I know that any modifications, any customizations, any new algorithms that I come up must beat this benchmark, because even a trivially simple algorithm like k nearest neighbor is getting me this performance. So in the community of machine learning, benchmarking is one of the most important ways of actually judging which algorithm to employ. So if you are going to apply machine learning for problems where you've got complex data sets or difficult things to learn, then it's best suggested that you first start off by doing a benchmark before starting off with some particular algorithm. So maybe there is some algorithm that you apply directly and you get 85%, and you say that you are getting great results. You are correct 85% of the time. But maybe if you had just done a benchmarking, you would have found that the benchmark is giving you 80%. That simply implies that even having used a lot of resources and consumed a lot of computational ability, your improvement in terms of performance is not that great. So I strongly suggest that if you're going to apply machine learning, you must follow this principle of benchmarking. Now, coming to neural networks, which have come to the fore in the last 10 years, 15 years, neural networks are very, very simple to understand. The idea is when you've got a neural network, you just feed the neural network the data that you have got. So if you remember that last example, I'll just feed in the age over here, which is numeric. I'll feed in the salary over here, which is also numeric. I'll feed in the gender over here, which is not necessarily numeric, but I can convert it to a numeric form. So if I can just write a male is a 1 and a female is a 0. So instead of writing a male or a female, I can just put in a value of 0 and 1. And I can put other numeric attributes over here. The important thing to remember is for a simple neural network, the inputs must be numeric. That is a very important thing to remember. The neural network is basically a sort of interconnections, the mathematics of which is simple, but it requires a little bit of understanding. But the idea is ultimately this entire thing in the middle that we are seeing, this entire thing that we are seeing over here is basically the model that we need to learn. And in the case of neural networks, these models are based on parameters which we call weights. So we need to find a weight for this particular connection, and we need to find a weight for this particular connection. The idea is we need to find the corresponding weight for all these interconnections. And if you can find these weights correctly, then when you feed in a data like this over here, when you feed in a data like this over here, it will make a correct prediction as to whether the credit rating should be high or the credit rating should be low. So the entire task of doing a neural network is to learn these weights that interconnect these computational blocks. Again, I don't want to get into a lot of detailed mathematics about neural networks. The only thing that I want to bring to the understanding over here is that neural networks are a very, very strong contender for doing supervised algorithms. And they have got even stronger with the advent of deep learning networks. So a simple neural network, as shown over here on the left, would have just maybe one layer of computational elements over here. See, I've got one layer of computational elements. But it was shown very early on, even in the 1980s, that with this one single layer, it is very difficult to come up with meaningful predictions on complex problems. Nowadays, we can actually have what we call deep learning neural networks, where you can have hundreds of layers over here, each of which contains hundreds of computational elements. These networks have tremendous learning capabilities. And when you feed in some kind of a numeric data over here, these deep learning networks, and they are called deep, not because they have got a lot of computational nodes, but because of the number of layers they have got. So you see, in this case, I've got 4 layers of computational nodes. But you can actually have 60, 70, even 100 layers nowadays. So these deep learning neural networks have tremendous computational learning capabilities, and once trained properly, their capability to predict things often outdoes even humans, even in complex tasks. The only issue is when you increase the number of layers and you increase the number of computational nodes, as you can see in this case, you can also see that the number of interconnections also increase. And for each interconnection that you can see in this drawing, we need to learn a weight, which becomes a huge computational challenge. So to train a really large deep learning network, you have to use a graphics processing unit, or you will need a large parallel system, something like a Spark or a PySpark environment. So this kind of a deep learning network, albeit it is very, once the model is learned, it's very useful, but for practical tasks, training them can be a challenge, right? Deep learning networks have one other thing that we want to bring to the fore. Instead of just taking in numeric values like we have been talking of so far, deep learning networks over the last 10-15 years, particularly due to the work of Jan LeCun, because of the work of Jan LeCun, nowadays we have got deep learning systems which can actually take as an input an image. And even though we are saying it's going to take an image as an input, the values that go in are just the pixel values. So basically, you will end up giving the RGB triplets or whatever form the color space is into this particular learning system. Interestingly, these networks can actually learn image features, and convolutional neural networks, these systems are called convolutional neural networks, have become tremendously powerful in predicting things about images. They can not only predict things about images, but they can also find things in images. And nowadays, you can also synthesize images using these convolutional neural networks. So we have gone from a place where we were predicting things to actually finding things in images. And now we have reached a stage where given a lot of images, you can synthesize new images. So which is again a tremendous step forward in terms of generating new data. So convolutional neural networks are deep learning networks that usually learn from images. It's not necessary that they have to learn from images. They can learn from a lot of other things. They can learn from text. They can learn from sequences, but they are most appreciated because they can learn from images, right? Now, the next thing that I just want to bring to your notice is a thing called transfer learning. If you've not heard of transfer learning, and let's say you've got a project in remote sensing where you think the project requires machine learning, and you also believe that you will require deep learning networks. Let's assume you have that stage. Then you need to take a call whether you need to actually train a deep learning model yourself, or you want to go for transfer learning. In many cases, transfer learning is a very, very attractive alternative to actually training a deep learning network. So what is transfer learning? Transfer learning allows us to borrow a model trained for some specific task to be used for a task that is different. So the idea is, let's assume someone somewhere sitting in a big company, something like Google or Microsoft, who have got huge infrastructure. These companies have already trained deep learning networks for a lot of tasks. And these models are now made available publicly. So as a common user, what you can do is, instead of trying to train your network for a specific task, you can borrow one of these models and apply that model for your own task. So that is a tremendous way of actually applying deep learning models very quickly onto a specific task. They neither required a lot of computational ability, and you also save on time. So I strongly suggest, if someone is looking at deep learning for their next project, or you think that deep learning is a wise alternative for something that you're doing, then instead of trying to train a neural network model, which sometimes we do out of ego, we say that we'll train our own model. But sometimes it makes more sense to actually go for transfer learning if people have already trained things for you. So that's what transfer learning is all about. Now, so we are now done with supervised learning, where the task, if you remember, was to predict some class label or some kind of a numeric value. The next type of task that is often done in a machine learning scenario is called unsupervised learning. And in unsupervised learning, the data that you get is unlabeled. So I don't get those labels that we were seeing previously. So you'll not get a data that says that this is a spam email and this is a ham email. You'll not get a data that says that this is wet soil and this is clay soil. So that kind of data is not available. You're just given the data, right? And the system has to learn something about this particular data without any kind of supervision. But let's say I just give you this data and there is no label attached to any of these individuals that you see in this photo. So what can you actually learn out of a data like this? So what we can actually learn from data out of this, quite a few things actually. One thing that you can learn from a data like this is a task called clustering, where you can try to group individuals or data items based on similarity or mutual similarity. So you can actually try to group them into different groups. And this is a task that is called clustering. And this is something I'm pretty sure in the remote sensing community, this is done a lot. But as you can see that we go about doing clustering without really having to have knowledge about the individual labels that exist for these particular data items. The actual task of clustering is always done based on the similarity or the distance measure between individual items. So one of the primary tasks that is done in non-supervised or unsupervised machine learning is clustering. Another task that is often done in machine learning in the unsupervised or non-supervised sense is called anomaly detection, where given some kind of a data set that seems to have a very close sense of neighborhood, in anomaly detection, we try to detect some data that seems to be quite different from the rest of the data. So if this data set is given with all the dots available, and if you're now given this cross over here, and you're asked whether this particular instance of the data is something that is reasonable, your answer would be yes, because it seems to fit right into this particular distribution. On the other hand, if you're given some data over here, then your answer would be this is possibly an outlier. This is possibly an outlier because it doesn't seem to fit the distribution, right? So outlier analysis is another thing that is often done using non-labeled or unsupervised data. So this is the second task that we do. So some of the common methods of doing unsupervised clustering or unsupervised tasks in machine learning, you do clustering using methods like k-means and dbScan and hierarchical cluster analysis. There are so many other methods. You can do DenClue, you can do optics, you can do many other methods. You can do anomaly detection using one class SVM, you can do isolation forest. These methods are specific for doing outlier analysis. And then you have got tasks like association rule mining, which can be done using methods like a priori, eclat, and so on and so forth. You can do FP tree over here also. So all these tasks, whether you're doing clustering or whether you're doing anomaly detection or whether you're doing association rule mining, these are all unsupervised, right? Now, another kind of task, and I think this is gaining a lot of prominence in recent times, is to do semi-supervised learning. So in semi-supervised learning, the task becomes even more challenging. The reason for that is, even though you have a lot of data, as you can see, you've got a lot of data over here, but unfortunately, you only know the class labels for a few of the data items that are available. So you do not know the class labels for most of the data. So you know the class labels for these squares, for these triangles, you know the class labels for these, but you don't know the class labels for most of the other items. Given this kind of a scenario where the class label is known for a few items, but not known for the majority of the items, your task in semi-supervised learning is to predict the class for a new data item. This is a very, very challenging task. And if you have gone, if anyone has gone to Facebook or you have gone to Instagram, and if you have looked at the concept of photo tagging, which is something that we have all got used to recently, then this is one of the primary applications of semi-supervised learning. Remember what we do in a photo tagging scenario. So let's say if there is one photo and there is some individual over there, as a person, as a user, you go and label this one photo as A. So you've just labeled this person as A in one photograph. But now the algorithm is good enough so that when he goes to another photo and he sees the same person, he can recognize that this and this are the same person, and the photo will automatically tag this as A, even though this has not been labeled by a human. The photo tagging is one of the most important applications of semi-supervised learning, right? So as I often tell my students, There are so many applications of machine learning that we use every day, and we are not even aware that this is a particular application that we are doing. So people will do photo tagging, but even my CS students would not know that this is basically semi-supervised. Right? Reinforcement learning is even one step further on, and in reinforcement learning, we actually have the concept of an agent, and we have the concept of policy. So rather than getting into the theoretical description, let's just look at an example. So the agent is actually something that is taking a decision. So this is the learning agent. So this is the learning agent. And if the decision he takes is a bad one, then we actually penalize him by giving him some negative points. And if the agent actually takes a bad decision, because of the penalty that is given, he will try to avoid taking the same decision the next time. So that is how reinforcement learning works, where an agent is made to take a decision, and once the decision has been taken, the agent is actually penalized or rewarded for taking that decision. One of the prime applications of this particular work is robots that actually work. So if you've seen any robo that is walking, then that's the principal way of applying reinforcement learning, because as the robo works and there is some kind of an obstacle in front of him, if he moves and hits this obstacle, then he will be given some negative points. But if he is able to go in a different direction, then he's given some positive points. And then if he wants to go in this direction and evades the obstacle and comes back, then he's given even more positive points. So that is the basic concept of doing reinforcement learning. Right, so you've got supervised learning, you've got non-supervised, you've got semi-supervised, and you've also got reinforcement learning. All these actually make up the gamut of machine learning. Right. As I said very early on, there are two different, there are other ways of categorizing machine learning. One way is to talk of the difference of doing batch learning and talk of the difference of doing online learning. So in a batch learning scenario, the entire data that you have got at your disposal, the entire data is fed into the system at one point in time. So your machine learning system, whatever system this is given the entire data to work with. While this is very good in some cases, the batch learning system is a big challenge. One, you need a lot of memory. Two, you need a lot of computational ability because you're working with very large data sets. So for a common person, maybe working on a desktop that we have got in our offices, this batch learning mode may not be such a great alternative if you've got very large data. If you try to feed your entire data into the system at one point in time, then your system is most likely going to crash or may hang. Compared to doing batch learning, a much more interesting and good alternative is to do online learning. So I'll just explain online learning with this diagram over here. So in online learning, what we do is we've still got a lot of data to work with. We've still got a lot of data. But what we do now is we partition the data into small fragments or partitions. And so when the machine learning problem is to be trained, instead of giving this entire data, we only feed it a fragment of the data. And the machine actually learns based on this first fragment. Once the learning is complete with this first fragment, we now feed it this second fragment of the data. And what should be the size of the fragment completely depends on what is the problem. But usually the idea is to partition the data into small batches. So in machine learning, it's very common to hear of something called batch size. And when you see this word batch size, the implication is that if you've got a very large data set, the algorithm actually tries to get the data in, not in its entirety, but in batches. And the size of this batch, let's say K, is known as the batch size. So assuming that you've got let's say you've got 1,000 data items. If you split it into, let's say, 4 distinct partitions, then you end up with 250 data items in each partition, and that's your batch size. So whenever you're looking at solving a problem in whatever context, and you think that your data is very, very large, it is immediately essential that you start thinking in terms of doing online learning rather than batch learning. Batch learning is fine if you've got a small amount of data that you want to read in and just prototype your algorithm to see if it is working, then it's fine. But for production environments, it is very difficult to actually come with meaningful batch learning systems. For production environment, it always makes sense to break up your data and then feed the data into the system in pieces, right? One other way of classifying machine learning algorithms is whether these machine learning algorithms are going to be instance-based or they are going to be model-based. So, as I said previously, in an instance-based system, these systems are often known as lazy learning systems. The reason why we call them as lazy learning systems is because these systems will not learn any models at all. They will not learn any models. So every time you actually give some data as an input, the only thing that this system does is actually store the data, and it does nothing else. You give some data to the system, it doesn't learn anything, it doesn't do anything with the data, just stores it. Finally, when the time comes to predict something, so let's say now that the data is available and this is the new instance, and you're trying to say, can you tell me what is the label of this particular instance? Is this a square or is this a triangle? Now the system actually does the only computation it has to do. And what it does in this case is it measures the distance from this new instance to the neighbors. And let's say you decide that the number of neighbors you're going to consider is 3. So take this new instance and find the 3 nearest neighbors. So it turns out that this is one of the nearest neighbors, this is the other nearest neighbor, and this is the other nearest neighbor. Out of these 3, we find that 2 are triangles and 1 is a square. So you now take a poll, you now take a vote. And you see, because 2 are triangles, you say that your prediction for this new instance is going to be a triangle. And that's the way this system works. It doesn't learn anything. It just stores the data and makes a computation on the fly. Compared to this, you've got model-based systems where once the data is made available, the system actually learns some kind of a model. So this dashed line that you've got over here is learned by the system. And then if you've got a new instance, if a new instance comes, it checks whether it's to the left of the model or to the right of the model and makes a prediction. So in these systems, which we call as model-based, the model being this demarcation that we have learned, when the prediction time comes, it's very, very fast because the model is already known. But when you're training the data, this takes a long time because this demarcation, this segregation has to be learned, and the learning requires a lot of data. So sometimes it's interesting to decide whether you are going to go for an instance-based learning system or you're going to go for a model-based learning system. The decision lies on what is the amount of prediction time you've got. If you believe that the time of prediction that you've got is almost run time, you have to do a prediction that is very, very fast, then you must go for a model-based system. While on the other hand, if you believe that when you're making a prediction, you've got some time at your disposal, then it often makes sense to go for an instance-based model. But ultimately, this decision is domain-driven and problem-driven. Right. Very quickly, I'll go through what we understand by the measures of performance. So the machine learning community is something that is very, very mathematically inclined. And every time that you come up with some kind of a application for a particular machine learning problem, you must have some very well-defined, well-delineated measures of performance. So in the case of doing supervised learning, and remember in supervised learning, we actually do predictions of labels. There are some very, very common ways of measuring how good or bad your classification algorithm was. And these measures are usually the measures of accuracy, precision, recall, F-score, area under curve, ROC, and so on and so forth. There are many typical measures for measuring the system and how efficient the system was. Right? Technically, all these measures that you see on the left-hand side can be computed from a matrix that is called a confusion matrix. So you can use a confusion matrix to immediately calculate what are the counts for your accuracy, precision, recall, and so on and so forth. The confusion matrix is very, very simple to understand, assuming that you have got some predictions that you have made and you actually know the labels. You make a comparison of how many you got right and how many you got wrong. So I'll keep the mathematics out of this, but just in a layman's sense, what we are doing is, if you look at this number over here, in fact, let's start off by looking at this number over here. You see, in this case, you predicted a label of no, and the actual label was also no. For 50 items, your prediction matched the actual value. And if you look at these 100 over here, then you predicted yes for them, and the actual values were also yes. So you got these 100 items right. So you got these right over here, and you got these right over here. So you can do some mathematics based on this. However, if you look at this number 10 over here, this is an error because you predicted yes, but the actual value was a no. So that's an error you did over here. And similarly, you got 5 over here wrong because you predicted no for these, but the actual value was yes. So you got these 5 also wrong. So out of the 165 data items that you've got, you got 150 right, and you got 15 wrong. Based on this, you can do a count of all these measures. The actual mathematics I'll just leave for the time being, but it should be easy to understand that accuracy should easily be defined as 150 out of 165, because you can see that you got 150 right out of a total of 165. So that is the definition for accuracy, right? However, it's very common if you go through literature and if you look at a lot of the papers that are written, many people actually judge a machine learning system based only on the accuracy. But this is a complete fallacy. You should not be judging a machine learning system only on accuracy, because in many cases, accuracy is a very, very biased indicator. You must remove the bias in the accuracy by looking at other models like precision recall and F-score and so on and so forth. I'll not do the mathematics for precision recall F-score over here, but you should remember that if you're only looking at accuracy, then you're probably getting a biased value or a biased view of how good or bad your machine learning algorithm is, right? If you're going to do some measures of accuracy for unsupervised learning, then you've got a lot of other choices. So you're doing some kind of a clustering algorithm, then these are the choices you've got. Again, the mathematics for these are very, very simple. The basic idea for most of these, is if you have done a cluster, then the idea is the cluster should be very compact. So any cluster should be very compact, while two separate clusters should be as far as possible away from each other. So what you're looking at, a good clustering algorithm should make very compact clusters. They should make very compact clusters, and these clusters should be very far from each other.
Abhijit, can you go back to one slide?
One slide, sir. Okay, one slide.
Go back. Yeah.
Right, sir.
Here 50 is the false, no, true or negative.
So this 50 over here,
It is true negative.
so these are false negatives, sir. The reason why they are false negatives is, sir, because you predicted no. So that no is a negative and you got them wrong. So this is a false. So that's a false negative.
No, but the actually also no.
So not this one, sir. Not this one, sir.
Actually no, predicted is no. That means both are matching.
So this not this case, sir. This case is obviously a true negative, sir. This is a true negative.
Yeah, that's what I mean. It's a true negative.
This is a true negative and this is a true positive.
That's what I wanted to see. Yeah.
This is true negative, true positive. But if you look at this particular instance, you predicted a yes. So this is a false positive, sir, because
false positive, and this one is false negative.
This is a false negative.
False negative, yeah.
Right, sir. So this is again, I think Patel sir asked this question early on. One of the important things of doing a machine learning algorithm is to come up with a very good model selection. Remember, we talked at some point of three things. We talked of a training set, we talked of a validation set, and we also talked of a test set. And if I can quickly remind the audience, the train set is the set from which you are learning. The validation set is the set of data that actually measures the improvement in performance as you are learning. And the test set is the final set of data on which you want to get the final results, or as how good or bad the algorithm is. Now, what would be the different ways of creating these train set, validation set and test set? The first way that we do it is by using a method called test train split. So in a test train split, if I assume that this is my original data, what we'll do is we'll split the data usually in the ratio of 70 is to 20 is to 10. Now that number is not fixed. You can choose whatever ratio you want, but usually the industry standard is to go for 70, 20 and 10. So 70% of the data would go into the trained data, 20% would go into the validation data, and 10% would go into the test data. This over here is the test data, right? The only thing that you must ensure is that this training data has a very good shuffle ratio. Now, what is the shuffle ratio? Let us say you're trying to predict 3 class labels, 1, 2, and 3. You must ensure that this training data is not biased in the sense that if the training data only contains the labels 1, then there is absolutely no way it can learn that there are 3 labels. We must ensure that the shuffle ratio in your training data is good and it has got a good mixture of all the class labels that I need to learn. So this train test split is one way of doing a model selection. The other way of doing a model selection is called k-fold training, where your entire data is partitioned into partition 1, partition 2, and partition k. And then what you do is you train your model. Now this is very interesting. You train your model on partition 1 going up to partition k minus 1. So you train your model on this data. So that's your train set now. And then you make your predictions for the data set pk, the last one. Then what you do is you train your data on P2 going up to Pk. And now you make your predictions for P1. You see, every time we are going to use n minus 1 sets to be the training set and make your prediction on one of the sets. So this is another way of doing model selection, and this one is called k-fold training. Usually for practical purposes in production environments, k-fold training usually wins. This is probably the best way of doing it. One of the advancements of doing k-fold training is to use a method called holdout method. So what's a holdout method? In the holdout method, instead of choosing partitions of size P1, P2, and Pk where the sizes are equal, what we do is we choose n minus 1 rows as our training set. So if there are n rows in the training data, we choose n minus 1 as our training data and make our validation set the one remaining row. In the next iteration, we choose a different n minus 1 and take the 1 as the prediction. So in the holdout method, in each iteration, we train on n minus 1 data and predict 1. And the holdout method is also very effective, albeit it is very time consuming. So if you are looking at a very good learning outcome, you will probably go for holdout method. If you're trying to go very fast, then you will probably go for train test split. If you want a good balance of both, then you will go for k-fold training. But these are the different ways in which you can actually generate your training set, your test set, and your validation set. All these methods are commonly employed, right? So if you're doing a prototype, if you're just trying to see if your algorithm is going to run actually, then my suggestion is you go for train test split. If you are in production environment and you want to make your algorithm available for public use, then I suggest you go for k-fold training. Finally, I think this probably is coming to the end of the first segment. There is this unique problem called the bias variance problem. One of the things that we must learn to appreciate is the machine learning model that you are building is actually learning from the train set. So it is learning from the training set, right? So there is a possibility that the machine learning algorithm that you have got overlearns the training set. Let's see what I mean by that. So let's say your original data is these dots. And if your machine learning algorithm has not yet learned the model, it is yet to learn the full model. Maybe it predicts something like this for this. As you can clearly see, this is not learning the model because the actual data has got this shape. But your prediction turns out to be a very, very linear kind of a shape. This is called underfitting the data. Right? Just the opposite side of the spectrum, you've got overfitting the data, where you've got the model has overlearned the particular training data that you fed it and has actually learned the data absolutely in the sense it exists. This is called overfitting. You have basically overlearned the data. Right? This is also a very bad thing. What I really need is a very generic learning, something like this. This is the perfect learning for this given data where the model has neither overfit nor underfit the data. One of the things, one of the challenges of doing machine learning is when should your algorithm stop learning? And this decision is often taken by this bias variance problem. When you can actually measure the fact that your algorithm has fit the data correctly, neither underfitting it nor overfitting it, then we usually say that we'll stop learning. Right. So
this
again,
sir, excuse me. So this overfit data distribution is different than underfit optimal one.
Yes, this is different, sir. In the overfit data, this is often called the high variance problem. This is called the high variance problem. What usually happens is because the data is learning too much of the original training data, there is a possibility that if your training data contains some outliers or the training data contains some bad data, this particular learning will be highly governed by that outlier. So it is important that your data should not learn the specific data item. It should not learn the specific data item. What I should learn is the general trend. So if you're starting to learn the specific data items, then that specific data item that you're learning from could well be an outlier which will completely collapse your model. That's the reason we should always try to learn the general trend rather than the specific data. In this first case, as you can see, I have not even learned what is the model has just started learning because it has not even seen that the data has got this two-dimensional nature. It's just gone straight. So that is underfitting. This one over here is completely learning specific data points, which is overfitting. And we should avoid both of these. And there is a lot of intricate mathematics that can exactly tell you whether your algorithm has fit or underfit or overfit the data. But again, that is for another day. The basic idea is nowadays, as I'll be able to demonstrate, I guess, there are lots of tools available where you will not be required to do that kind of a mathematical traction. The tools will tell you whether you are in the right direction or in the wrong direction.
Okay. Thank you.
Now, so now that we have talked in such glowing terms about machine learning, does it always win? The answer is obviously no. Nothing wins all the time. There is no free lunch. So what are the main challenges to machine learning? The biggest challenge is insufficient quantity of data. And when I say insufficient quantity of data, this is particularly true for people like us sitting in academic institutes. We do not have access to data that is very voluminous. Maybe we often have data that is very sparse. So for us, it becomes a big challenge to actually get a machine learning algorithm to learn well. This is a typical scenario where I strongly suggest we look at the alternative of doing transfer learning. Borrow from someone else, right? Sometimes the data you are actually training on may be non-representative. So this is usually true when you've got huge volumes of data and you cannot manually know whether this data is actually representing the correct classes that you want to predict. One typical example is that let's say you've got hundreds and thousands of books. Let's say you've got 1,000 books and you're supposed to predict whether this book is a comedy or the book is a tragedy. And unfortunately, it turns out that in the training data, let's say you end up with 900 comedies and only 10 tragedies. Now that's a bad representation because the machine basically ends up learning that irrespective of what book I am given, it is best to say it's a comedy. Because most of the books that it learns from turns out to be a comedy. So that's a bad way of learning. Your data must contain a good mix of the things you want it to learn. Right? So poor quality data and irrelevant features are pretty much implying the same thing. And then you should definitely avoid overfitting and underfitting the data. And as I said, there are ways and means of finding out whether your data is underfitting or overfitting the data. So when you're doing a machine learning algorithm, if someone comes to me and says that I need an algorithm to solve this particular problem, the first thing that I should be asking him is, do you have sufficient data? And then I should be asking if the data is clean, if if he has a good understanding that the data is a representative data, not anomalous data. If his answer to these questions are true, then we can immediately apply some kind of a machine learning algorithm. So sometimes I find that people, particularly who do not have a lot of understanding of the theoretical context of machine learning, they will probably start a machine learning algorithm applied to some data, and they will find that the results are not what they were expecting, maybe even poorer than what they were getting with their traditional methods. We must appreciate why the machine is not learning, and then you must try to rectify on those factors. Right? So I think that brings me to the end of the first segment. I don't know how much time I've got. For this second segment, I had actually outlined a little bit of Python code so that you can see how simple machine learning is from the context of programming in Python. I think it's best to quickly go through this section because I'll be running out of time. So Python is a language which I strongly suggest that people pick up for machine learning. And when I say I strongly suggest, I'm not talking of the CS or the IT community. Anyone who wants to apply machine learning to his problems, I think Python is a very, very good programming language to learn.
Sir, excuse me, sir. I have, hello.
Please go ahead.
Yeah. I have one query, sir.
Right.
Actually, I got the confusion about online learning, sir,
Right.
after seeing your PPTs. So, could you give me the difference between mini batch learning as well as online learning?
Right. So, mini batch is just one way of doing online learning. When you've got a mini batch system, what you're basically doing is you're partitioning your data into small batches, right?
Yeah.
And when you're partitioning your data into batches, irrespective of what is the size that you're choosing, that is basically an online learning system. But the idea why we use that word mini batch learning is because of the fact that there can be other ways of doing online learning. Say, for example, if you have a system that is actually learning from some kind of an input that is coming from the stock exchange. Now the stock exchange is going to update itself at every instance in time. So that is also a way of doing online learning because the data is changing and the data is coming to you in small windows. So maybe you get the stock closing price for the last hour. So that's a window. So that is also an online system, but that's not a mini batch. That's not a mini batch.
In batch learning, is it data will change every time? So because as per my knowledge, in batch learning data, you have lot of millions of data is there. So for that computational purpose, you are doing mini batch. So the data is, I think, static only. But in online learning, data is changing every time. So, if anything, please correct me. So that
is one way of looking at it. If you have got some data and that data is partitioned into different sets, and every time the machine takes an iteration, you give it a different set, then we can call it online learning as well. If you're saying that the data has to be different in every single iteration, then that is also online learning. The idea is that the data that you are actually giving the system should not be the entire data. As long as you're not feeding the entire data, then it is online learning. And in some cases, the entire data may never be available. Say, for example, in the stock exchange example, that is an endless stream of data. In some cases.
Okay, you mean that online learning is a part of batch learning? You are saying that?
Yes, definitely.
Yeah. So one more thing, sir. Because you mentioned everything, because as per my knowledge, but you did not mention stochastic learning. So is there any opinion on that?
Once if I get into regression or if I get into stochastic learning, the reason why we avoid that over here is because if I talk stochastic learning and randomness, then it brings in a little bit of mathematics, right? And in this particular thing, if I try to explain how to do a stochastic sampling from a particular data set, that will eventually it will require a little bit of mathematics.
Yeah.
So that is the reason why that's the reason why I did not get into stochastic learning.
Very nicely. So I don't want to interrupt you because I raised the question because you gave batch learning as well as online learning. Right. You forgot about stochastic learning. That's what I raised.
It's perfectly fine. Please, the questions actually make this a more interactive thing. No? So you must ask the questions. Even if you see if you know the mathematics that goes behind these learning systems, you'll find that in all my descriptions that I've done so far, I have completely avoided mathematics. Even in the confusion matrix, I didn't get into saying that true positive divided by true. So I just avoided the mathematics so that we can keep this at a slightly more generic level.
Yeah. Thank you, sir. Thank you.
Right. So very nice of you to just intervene and just make this an interactive session. So I'll just get into the Python part of things over here. Very quickly, the reason why I find Python is a very good choice for starting off with machine learning if there is a community that wants to use it, because it's general purpose. You can apply it for anything from image processing to machine learning to writing websites. It can be applied for any task. So if you're doing a project and you have got a machine learning backend and you want to come up with, let's say, a front end which has to be written on a website, you can use Python for the website as well as for the backend. You can write a machine learning module and write the website separately. So Python is very general purpose. It is too simple. I often hear students saying that Python is a new language. How do we learn it? I just request everyone to give it a try. It is too simple. At least to get started off, you can spend 10 days and I'm pretty sure you all will yourself admit that you all are feeling very good about how simple the language is. It is interactive. You don't have to wait a long time to see results. You can write a small piece of code, you can run that code and you can see the results immediately. This particular aspect of Python makes it very attractive for machine learning. Write some code, see if it worked. If it doesn't work, change that piece of code. So it's very interactive. It's also very easy to debug because there's a lot of debug support. And then from the machine learning perspective, it has got huge community support. So what do I mean by community support is it is impossible for us as individuals to know and code every single aspect of machine learning. But in Python, you will find that there is a huge community that is already coding a lot of the algorithms that we end up requiring. So for you, it becomes trivially simple to just bring those algorithms into a program and get them to execute on your particular data. So you don't really have to go and write machine learning algorithms. And that is one of the reasons why I find Python so very endearing. Even for the toughest task, even if I'm training a convolutional neural network, I'll find that people have already written all that stuff. I'm just using what others have written. So that is the reason why that huge community support is one of the USPs of doing Python, right? And then one of the other, maybe not that prominent, but one of the reasons why I think Python is something that you should really try out is because the IDE support that it's got. IDE actually stands for Integrated Development Environment. And that means you've got very good places, very good software where you can actually go and write your code. And these IDEs are so advanced that they will suggest you a lot of things. They will have a lot of intelligence. If you start writing some wrong piece of code, they will tell you. If you're unsure what is the next thing to write, they will tell you that also. That kind of an IDE support in Python is very good. That's the reason why if you're starting off with machine learning and you want to write code for machine learning, then Python is a very, very good choice, right? Now, if you're going to write something in Python and if it's going to be specific to machine learning, then usually I break it up into these segments. So if I take a machine learning Python class, so if I go into a sessional and I've got a group of PG students and let's say I teach them Python for machine learning specific to that, I'll probably break the session up into these segments. So I'll look at data acquisition. I will look at appreciating the data. What is the data telling me? I will look at pre-processing the data so that it's more into a form that is amenable for machine learning. I will try to visualize the data to see if there are any trends that I can find out. I will apply some machine learning algorithm to it. And finally, I will try to present the results. So typically, if I'm making a session on machine learning, Python-based machine learning, then I will try to break it up into these particular subdomains, right? I'm just speeding up a little bit because I think I'm running out of time and Rathod sir may not appreciate that. So I'll just speed up a little bit over here. So now I already said of the community support that I was talking of. And if you're doing machine learning in Python, then some of the packages that you must be aware of are these packages. So NumPy, Pandas, scikit-learn, Matplotlib, Seaborn, scikit-image. The names may be new to you, but I can assure you that these packages are trivially easy to use. Once you know why this package is required and what is the extra functionality that this particular package brings to the table, you will find that you cannot write code without thinking of these things. So every time you've got a task, you will automatically start thinking that I should have Pandas for this, I should have NumPy for this. So NumPy is basically Python's numerical package. So anytime we are doing anything that's numeric, look for NumPy. Pandas is basically Python's data handling system. So if you've got a lot of data and you want to work with it easily, then it should be Pandas that you're looking at. Scikit-learn is an exceptionally good machine learning package. So that is specific to machine learning. Matplotlib and Seaborn are great visualization packages. They have got exceptional visualization capabilities. Scikit-image is actually an image processing package, and if you are trying to bring in image processing into your project, which may be the case in remote sensing, then scikit-image is a great choice. Obviously, there are hundreds and thousands of other packages. Like, for example, in image processing, you can possibly look at OpenCV, or you can look at Mautas and things like that. But this small set that I've presented over here, if I'm writing my machine learning projects in Python, I usually find that this is sufficient for me. And most of these would be very, very easy to use. Right. So quickly, I'll go through this. A typical Python program, as I said, this is going to be very, very easy to write, actually. There are a couple of things I would want to highlight. One, you should be able to import packages written by others. So you see, I'm not going to write everything of my own. I'm going to bring in packages written by others. That is one of the core points of doing Python programming. Do not try to write everything of your own. Just get others people code into your program. The other thing that I keep on saying is Python is very, very simple to write. If you're thinking of something in English, then most likely the syntax is going to be the same. Say, for example, if you just write print hello world, it will print hello world. Or if you just say print 10 plus 20, it will print 30. So essentially, I cannot teach the syntax of Python in a session like this. What I can tell you is that if you're thinking in terms of simplicity, then Python is almost unmatched. Right. Now, one of the things that we must start off is by bringing data into your programs. If you cannot read data into your programs, then it's very unlikely that you will be able to process it. Python is absolutely fascinating in terms of the kind of data it can import. So in this particular example, you see that I'm reading a CSV file. And once you have read that CSV file, you can immediately see the contents of the CSV file. So if you've got some file stored in a CSV file on your hard disk, you can just read it directly into your particular system. And you can also specify what should be the name of the different features. So you see, this is feature 1, feature 2, feature 3, feature 4, and then the class label. You can manipulate the data in whatever way you want. You can even read data from the internet directly. So you see, I'm reading this data from the internet directly. So no issues with that. And I keep on repeating this, just look at how much code I have written to get something done. I have read a file residing on the internet into my Python program, all in 3 lines, in fact 2 lines, because this third line over here is just displaying the data. With 2 lines of code, I've been able to get data from the internet onto my system. So that's the kind of power that Python brings, right? You can even read data in small sizes if you want. You don't have to read the entire data, something that we were discussing previously. You don't have to read the entire data in at the same time. You can just read it in pieces. So you see, in this case, I've given a chunk size of 10, and I've just read in 10 pieces of data. I can then read in the next 10 pieces and the next 10 pieces, so on and so forth, till I'm finished with all the data. Right? You can directly read in images from whatever website you want. So I just went to the Mosam website and I just read an image directly into Python. And again, you can see that it just took me 2 lines. So these are the only 2 lines. I have to specify the URL where the data is residing, and I can actually read it in directly. And if you are able to write some kind of for loops, or you can write some simple loops, then you can actually loop through an entire website and pick every image that is there on the website, and you can end up with a set of images. So I can read that. You can pre-process data. So if you've got some data set like this on the left, you can immediately get a lot of statistics about the data. So if you just see for the first feature, if you look at this first feature over here, immediately with one command, I can find out what's the mean of the data, what's the standard deviation, what's the minimum value of the data, what's the 25th quartile, what is the 50th quartile, 75th quartile, what's the largest value, everything in one command. So immediately when you're analyzing data and you want to get ready to do some machine learning, pre-processing is critical, and Python specializes in that. You can immediately start working and finding out simple things about the data. You can query the data. Mark how simple the syntax is. If you've got a feature over here, and this entire data set over here is called something over here, I can just say that for the data set, this is the feature, just tell me the mean value. So I keep on repeating myself that it's simplicity that drives people towards Python. You don't really have to go and write code and write for loops for everything. You just basically end up querying the data. You can find the standard deviation, you can find the quantile, whatever you want. Right. Also, you can immediately find out the correlation between features. You can find out correlation between the data. So I say that for the data that is available on the left, take feature 1, take feature 2, find the correlation. And you can see that feature 1 and feature 2 are negatively correlated. So they have got this negative correlation. So when one is increasing, the other is decreasing, but to a very small extent, but it's only 0.1. So you can immediately do this kind of a processing in Python on data, and you can get a feel of what the data is actually like before you start working with it. Okay. In this particular case, you see that I have done the correlation for the entire data for all the 4 features. So I found the correlation between all the 4 features. And it seems that feature 4 and feature 1 are highly correlated because the value is 0.8. This kind of a descriptive statistical analysis of data is very important for the machine learning community. And these examples that I'm doing are just basically scratching the surface. You have hundreds of such methods available. Sometimes you would want to actually scale the data. So you start off with some data like this, which is in a form which actually varies over a very large domain range. But you can just use simple methods in Python, and you can just scale the data in whatever way you want it. So this data has now been mean subtracted. So from the actual value, I've subtracted the mean and divided it by the variance. And all that has been done by using just this one line. So this is the kind of feature set that is available in Python. I'm not saying it's not available in other languages. So MATLAB or R or S will have the same kind of functionality. But I think Python has the simplest interface to work with. Right. So again, the same kind of thing. You can even reduce data very, very simply. So if you've got a data that has got 4, 5, 10 different attributes, you can do a principal component analysis and reduce it to whatever number of components you want. So in this case, I just want it to be reduced to 2 components. And that's the 2 components that you've got. So if you're sitting inside some kind of software which does all this, you will find that that software is actually maybe a paid software, or is a very, very complex software that uses a lot of computational ability. But Python is free and it has all these features built into it. Data visualization is possibly Python's strongest point. You can visualize data in whatever way you want. If you want to see histograms, that's available. If you want to see scatter plots, that's available. If you want to see multiple histograms on multiple features at the same time, that's available. You want to see 3D plots of data, that is available. You want to see the data along with their distributions, that is available. Whatever you can think of. I cannot think of one thing that Python cannot do. If you want to see an overlapping set of histograms, that is available. So data visualization is really one of the strongest feature sets of Python. Now, this is where I want to show the machine learning ability of the programming language. Most of these machine learning abilities coming from this package called scikit-learn. And you see, given some data, I wanted to cluster the data. And the only thing that I had to do was specify how many clusters I really wanted. And then basically, I just said that do the clustering for me. Just 2 lines. So this is what I keep on telling my students, that when you're with Python and you've got this huge community support, you can actually write a lot of, you can get a lot of functionality out of this language out by writing very few lines of code. Now this may not be ideal when you're trying to deploy a system, but when you're trying to prototype a system, this is absolutely essential. So you see, I wanted 3 clusters. This was the data, and it found 3 clusters absolutely beautifully over here. You see, the 3 clusters just came up. Also mark the fact how beautiful the visualization is. The visualization was done with this one line. I can do the same if you're trying to fit a linear curve to this particular data set. So if you've got some data set and you find that this data has some kind of an inclination in the positive direction, and you want to find the curve that fits this, then you again basically have to write one line. You can just say that you want to do a linear regression and just fit the curve, and you'll get the fit over here. Again, this is, as I say, the machine learning computational power that is available inside of MATLAB, inside Python, is absolutely unbelievable, right? Sometimes you actually want to do a classification scenario. So in this case, if you see, I have just done if you remember, we had talked of the k nearest neighbor classifier. So I'm now saying that can we try to predict a label using the 5 nearest neighbors? And you see, this is the prediction that I've got. This is the prediction I've got. And this is the actual data labels. And you will see that I've almost got all of them right. Even, as I said, anytime I use a k nearest neighbor algorithm like this, I usually use it for doing benchmarking. So this is only for benchmarking purposes. And even on benchmarking purposes, you see the accuracy in this very trivial data set, obviously a very trivial data set, but this is very, very good, right? If you're going to write a slightly more complex kind of classification, then you can actually not only write the classification, but you can also measure the performances. So you can find out the accuracy. It turns out to be 93% accurate. You can find precisions. You can find recall values, and you can also plot confusion matrix. All inside code that are not more than 1 or 2 lines. All of this is built inside Python. So not only write the machine learning algorithm, but also measure the performance, visualize, all from one programming language. Right? Now, over here, I try to design a simple neural network. The understanding is neural networks are very difficult to write. They are very difficult to write, and they're very difficult to train. So I thought that I'll just write a little bit of code to show that writing a full-fledged neural network in Python is hardly going to take any effort on the part of the programmer. This entire thing over here has nothing to do with neural network. If you see very carefully, I'm basically trying to just load the data and see what is the shape of the data, nothing else. The only interesting part is I've actually used a function called train test split. And remember, we have talked of train test split in the model selection. And I'm saying, why not use 80% of the data for the training, leaving 20% for the validation and test? So Python even has model selection methods built in. I go and train a neural network, a simple neural network. You see, that's my neural network, and I'm training it for 500 iterations. These are my predictions, and these were the actual class labels. And you'll find that the neural network is strong enough to make 100% prediction. Again, I don't want the audience over here to go and look at the code and the code I've written. Just look at the simplicity of what I've done. Just 2, 3, 4 lines, and I'm getting a full-fledged neural network to run for me, right? So what I want to finish off this presentation with is that so far I've been looking at machine learning from theoretical perspective, and I've also looked at machine learning from the Python perspective. I'm not really a remote sensing person, but I thought that since this is an audience that caters to the remote sensing vertical of things, why not try to apply some of these algorithms to some kind of a remote sensing problem? Does it work? So let's see if I can get something done over here. This first data set I just picked up from UCI, and it's called the StatLog data set. Now the StatLog data set, I'm pretty sure the audience would be much more enlightened about this kind of a data set than I am. But it seems that each row is made up of 36 pixel values. So this is one row. And for each of these rows, the last field is actually a prediction of what kind of a soil this is. You can go and look at that in case you've not seen this data set. It is available on this particular URL. So the idea is the data is to be interpreted like this. So there is one pixel at the center, and these are the 9 pixels that are surrounding it. And I've got the R plane, the G plane, the B plane, and the alpha plane. So each plane has got 9 pixels, and I've got 4 such planes. So that gives me a total of 36 values, and that's these 36. Based on this interpretation, this particular pixel at the center, is classified as something like wet soil or clay soil and so on and so forth. So 3 is probably, if I remember right, is clay. And 4 was, if I remember right, wet soil. So the idea was, given these image patches, and how many rows did I have? I had 4,435 rows to predict. So could I actually go and make a prediction based on this? So in my first model, what I did was I just wrote a simple neural network without even considering that this was an image. I just looked at those 36 attributes as numerical attributes. I did nothing else. I just wrote the data as if they were numerical attributes. I was not even considering it as an image. Even in that case, even with this small code, if you see all this part over here is just reading the data and just processing the data. The actual prediction part only happens over here. That's one line. And if you see, I got 84% accuracy on this data, even without considering it as an image, which it really is. So just running the code on it, just looking at it like a normal data set, I get 84% accuracy. In the next iteration, I thought, why not try to actually think of it as an image? So what I did was I actually converted it into red, green, and blue. I actually ignored the alpha channel because transparency did not play a role over here. So what I did was I converted these 36 pixels over here into an R, a G, and a B, and then concatenated them, superimposed them. So this is an example of one of the patches, and this is class 3. So this was clay, and you can see the color connotation. It is clayey. And then what I did is, now that this is an image, I thought that why not train it with a convolutional neural network? Because we've already said that convolutional neural networks tend to be very good when it's fed images. So I trained a convolutional neural network, and you see it was quite a large convolutional neural network. You see how many layers I've got? I've got so many layers over here. But to get that done, I only have to write this small code over here. So an entire convolutional neural network with just 6-7 lines of code. And if you see the number of model parameters, you remember we had talked of the parameters? The number of parameters that this model has to learn is in the tens and thousands over here. And yet, on my single laptop with a simple GPU, I was able to train it with an accuracy on the same data that is virtually reaching 94%. If you see, that's 90 over there. So training it without thinking of it as an image, I got 84%. When I actually converted it to an image, I could easily get to 94%. So this is the kind of power, and I'm not really a remote sensing person. I would not be able to engineer the features to make this a correct problem. I just looked at the data from the perspective of a computer scientist person and thought that why not train it? So this is where I think that the remote sensing community can really benefit from the machine learning paradigm. You would have a lot of domain knowledge which you can feed into these algorithms, and the results would be even better for your particular problems. Right? This is another thing I did. I just picked up from the Landsat repository. I just picked up some image, and I tried to write some Python code to cluster it. It took me 2 or 3 lines of code, and this is the case where I actually wrote the code for 2 clusters. And then this is where I've got 3 clusters, and then this is where I've got 4 clusters. So truth be told, all these 3 clusters I wrote yesterday night in half an hour's time, including putting it in this PPT and doing the visualization. So that's how simple things can be with Python when you're doing this machine learning kind of a thing. Right? So after I did this, the next thing that I thought that maybe I should be able to do is I should tell the community also about transfer learning. Rathod sir.
Yes.
I think it is 4:30. I've got 10 minutes. Can I go on for 10 minutes?
Yeah, for next 10 minutes.
Thank you, sir. Thank you. So I thought that I talked of transfer learning, and these data interpretations that I'm doing over here are actually not showing that power of transfer learning. So I thought that I will also show the audience a little bit of the features and facilities of doing transfer learning. So what I did was, I'll just see if I can get this to run actually. So what I did was, in the first instance, what I did was, I actually went and I used Mathematica for this because Mathematica makes this very easy. So what I did was, I actually searched Mathematica for a geo image. I'll just increase the size over here. So I just said that, can you find me a satellite image of BIT Mesra from a height of 500 meters? So it gave me this image. And then I said that, can you just cluster this into 3 components? So it clustered the image that I got over here into 3 components. So then I said that, can you actually colorize this based on machine learning? So what should be the appropriate color for each of these components? So there is this function inside Mathematica called colorize. And what I did was I applied the function colorize over here. And if you see, this is the colors that I got. So if you see very carefully, all these buildings over here have now been turned yellow. If you look at the buildings, and all the trees have gone blue. And this is such a good example of actually using visual interpretation. Even though I did not do it, from the image processing perspective, what I was thinking was, because of the clustering, these roads are now actually standing out beautifully. So maybe I can just apply the Howe transform or the RANSAC algorithm and actually find out which are the roads over here. So this image has actually made the road stand out beautifully. Right. So this was one thing that I did very quickly so that you can see the power that is available. Check it out. I'm not really writing any code over here. So people look at computer people and they think that we are always writing code. The paradigm has really shifted. It's more about knowing what is already available and using it rather than trying to code through this. Right. The next thing that I tried to do was, I thought that why not try to write a random classifier? So what I did in this case was, again, I'll go through the font and I will change the font over here. What I did was I actually did a web image search, and I said, can you give me 50 images of photographs of forests from satellites? I asked for 50 images of satellite photos of forests. So these were the results. Then I asked for, can you give me 50 images of the Sahara Desert? So obviously, if I just look at the Sahara Desert images, I don't know whether I can be, let me just see if I can show it. I got these images. I know that these are random images. I was just asking for a Google search, but I did that. What I did next was I just labeled these images. So all the forest images I labeled as F, and all the desert images I labeled as D. So you see, after the labeling, this image is now given a label of F. All this is not doing any, I am not doing any coding over here. I'm just trying to bring that thing into play over here. I'm doing what is essentially intuitive to me. After having labeled all this, what I did was I took a uniform data set, I added a uniform data set, and I said that why not classify this entire data set? Can I write a classifier that can actually find out that this is the image of a forest and this is the image of a desert? And then I just wrote a random classifier. And if you see, even on this very, very poor data set, without writing any code, I was able to get an accuracy of 75%. And the data set I brought in was not even a realistic data set. I just queried Google for some images. What I'm really trying to bring into play over here is the fact that with the kind of paradigms that are available and with the kind of software that is available, we can now prototype things very quickly. So if you need to submit a research proposal and you need a prototype that has to be done, it's not really about writing lengthy code for these results to be seen. You can do it very, very quickly nowadays, right? Then what I did was, in the third instance, what I thought was, can I actually do some kind of a depth measurement? And this is one of the examples of what I believe is a transfer learning. So what I did was, I actually imported a model that has already been written for depth. So I did not write this model because it's too complex. I just said that, can you give me a model that does depth learning? And there was a model that is already available on the repository. So what I did was I fetched that model and trained the model on this image. The model actually returned me a depth image. And then what I did was I just applied a little bit of processing to get a plot so that you can get a sense of this particular depth. And if you see, the depth is absolutely clearly visible. I don't know. So you see, the depth is absolutely clearly visible over here. So I did this. Obviously, I understand even from the image processing perspective, finding a depth model like this would require tremendous programming and would be beyond most of us. But in this case, I don't really have to go and write a depth program. I can just fetch in a model, train it on the, this model is already trained. So just get it to work on an image of your choice and get the output. In the final example that I actually did, I actually decided that can I use another model to do something that is slightly practical over here. So another model was available that is called Pix2Pix photo to street translation. So what I did was I just loaded that model, transfer learning. Took an image of this was an image of Mumbai. I had to go for a city where the roads were prominent. So this model actually takes a look at a satellite and can find out where the roads are. So I took an image of Mumbai from a height of 200 meters, ensured that the image was of small size. I did not want to have a lot of processing time. So the image is only 256 cross 256. That's the image of the satellite Mumbai. And then I applied the model that I had borrowed from the repository and asked it to find the roads. These were the roads it found. And if you look at the image, it seems pretty good. Again, the focus over here is not to write the code, but to know that this kind of a model is available so that you can borrow it. And these are all freely and publicly available. Right? So this is the kind of facility and feature set that is now available inside the community. Right. So I'll just try to go back. I guess that was the last slide I had. I had a thank you slide, but I missed it somewhere. So that brings me to the end of my presentation. Any questions?
Hello, sir. Am I audible?
Yes, yes, you're audible.
Sir, my name is Naima. Actually, sir, I have one doubt, sir. For the validation from the validation data set, we got the idea about how well our model behave or fit, how well our model fit. So, if you are if you are plotting validation curve and our training curve, for I think it's in the both the curves should be convergent well. Actually, I have answered in the lower epoch, if these two curves were just touching well, then it's going to divergent well. Is it acceptable, sir?
Acceptable to the point where you do not start to overfit. As soon as you start to overfit, see, if you have got I don't know whether I can draw it actually over here. I think, so if you, I don't know whether this is visible. Is this visible? Is this, okay, I did not start presenting now. Just give me 1 sec.
Okay, sir.
Is my screen visible?
Yes, sir. Now it's visible.
So,
Yes.
so let's say you've got you're trying to do a validation curve plot, or you're trying to do an accuracy curve plot. And let's say that's the number of EPOs. I'm assuming that people understand EPOs over here because this question has come up. And let's say the accuracy is over here. Let's say that's my accuracy on this axis. And let's say on your training set, the accuracy has gone like this. So you can see that your training accuracy is very, very good, right? But on your validation set, let's say your curve has gone like this.
Yes, sir.
And now you see that it's absolutely senseless to train beyond this point.
Yes, sir.
Because beyond this point, you're actually overfitting the data that was there in the train set. So if your curve is taking this kind of a shape, if you're taking this kind of a shape, then the only way going forward is either to regularize the data, which is a concept which I have not discussed in this presentation, or you will have to actually look at in some way contracting the model.
Or I can stop the learning with the lower epoch, right, sir?
You can stop it over here. If you can find out the elbow of your curve, you can stop at this point.
Loss curve. Okay, sir. So is it acceptable, sir, if I stop it early stopping?
Completely depends on what's your benchmark. So if the benchmark is already, let's say, at 90%, and if you see that you're overfitting at 90%, then it would not be advisable to stop. In that case, you must use regularization or dropout to actually see if you can improve the model.
Okay, sir. Okay, thank you, sir.
Sir, I have a couple of questions. If you would like to clarify, please.
Please.
Like for the underfitting and overfitting of the model, you said that the term the sufficient data. What do you actually mean by sufficient data?
In terms of machine learning, there is absolutely no way of saying sufficient data. My take on that is the more data you have got, the better it is. So when I say it is sufficient data, you can only talk of sufficiency in terms of how little data you have got. So there may be a scenario where you're trying to train a model and you've got, let's say, 10,000 instances or examples. And if you train on the 10,000 examples, you see that your data is actually underfitting the curve that is desired. In that case, your data is insufficient. So you must ensure, again, there are many examples in machine learning where you will find that the amount of data that you actually have is insufficient. You don't have the data. So that is the reason why people have got things like data augmentation that is required. Because without a large volume of data, machine learning algorithms are not really going to give expected results. So data augmentation is a technique by through which you actually synthesize data and then you append it to your existing data. So when I talk of sufficiency, I'm only talking in terms of how little data you've got. The more data you have got, you're not really going to be worse off, except in terms of computation.
Okay, sir. If we are talking about any classification problem, image classification problem, so is this more number of data is prescribing like more number of images, satellite images, or the more number of samples, training samples or validation samples?
When you're talking of sufficient data, you're always talking in terms of training samples.
Okay. Sir, another question is, in case of the neural networks, is there any limiting factor or any way to identify the number of hidden layers? How many
number
hidden
of
layers
hidden
do I need?
identification of number of hidden layers is quite easy actually. Let us say that you do not have I'll only give you a heuristic. Let us just think of every single computational node in a neural network as a small amount of memory, right? This is how I would go about telling a student how to actually come up with what is the correct number of layers. What I'll say is that if you look at every layer and if you look at every computational node as a memory unit, so when you keep on increasing the number of memory units, what you're basically doing in a way is whatever training data you're supplying to this model, because it has got more than required memory, it will actually memorize the training data. And when it starts to memorize the training data, invariably, it will actually start to overfit the data. And then you find that your accuracy curve will start to fall off. So as soon as you see that your accuracy curve is starting to fall off, what you should immediately think is that your model is too large, and then you should start to contract. Now, if you contract it to a very small size, the machine will not learn at all. Then you will find that irrespective of what the actual curve should be, your model is virtually a straight line. In which case you can understand that your model has just too little number of layers and number of nodes. Then you should increase.
Okay.
That's a heuristic.
Okay, sir. Sir, one more question. In case of supervised classification, which are certain points we should be careful about when training the image for better accuracy achievement?
Biggest issue that I find when training images is that people often start working with the RGB values. They will keep it at 255 and start working with it. First rule of thumb when working with deep learning and or neural networks is that the input values should be very, very small. Because again, the mathematics involved would be out of place over here. But the idea is that you should always start your images in a normalized form. So at least, if nothing else, then you should divide by 255 if that is the range you're talking of, so that the values are now at least contracted to be between 0 and 1. So that is one thing that you should always ensure. The second thing that you should ensure is that if you're the images that you're feeding in, if you're feeding them in as images, then you should ensure that you have already done a covariance test. If these images are very covariant, then you will feed a lot of images in, but the machine will not learn because the images are covariant.
Okay. Okay.
So a covariance test is very essential.
Okay. So are there any machine learning is frequently used for binary classification? So are there any drawbacks for any multi-class classification using the machine learning techniques?
No, nowadays, with once you have got the softmax function available, you can apply it to any number of class levels. It doesn't really make any difference.
Okay, sir. Thank you. Thank you, sir.
Thank you.
So I think now there are no questions. Is there any question?
The covariance problem is really a big problem in classification.
Yes, sir.
But maybe an intermediate step of PCA or CCA could be implemented before the classification.
Sir, PCA is often strongly suggested. The issue with PCA, sir, as we understand that is that it depends on the actual data. So every time you've got a new set of data, you will have to find the principal components again. If you're looking at something like independent components, then these are very computationally challenging. So that is one thing that often stops people from actually doing a PCA on a very large data set. Because ultimately, if you have to do the PCA every time the data changes. So that is one challenge that exists. But the fact is, if you've got a medium-sized data set, then PCA is a very good way of looking at of doing it.
Chaliye, we will keep learning from you.
Nice, sir.
Thank you, Professor Mustafi, for very lucid and enlightening lecture. And I hope that many of the participants will now come on this machine learning area and will apply all these machine learning techniques on remote sensing data as well. So thank you very much again for sparing your time for this session and benefiting our participants as well as ourselves. We also benefited out of your lecture. Definitely it was very, very interesting, I can say, and yeah, in-depth knowledge. So thank you. Let's conclude today's day 3rd the third session of the day third. So tomorrow we again have 3 technical sessions participants. So please join in time, and very hope that the coming session will be interesting again, like this session. So thank you, Professor Musti, again. On very short notice, you agreed to deliver this lecture. Thank you. Thank you.
Okay.
Really thankful to you. Thank you.
Thank you, sir.
Horo.